last week from Santa Rosa Junior College. He's not here, but thanks, John. Good job. If anybody missed the talk last week, John has agreed to be the speaker at the 56th annual Redwood Empire Mathematics Tournament. He's going to give the same talk on Saturday, March 7th. Okay. Next week we have Professor Yoon Kim from HSU Mathematics and in particular statistics. Yoon, are you here? Yes, he's right down there. He's going to put together right before our very eyes FAQ. He will address frequently asked questions in elementary statistics. Is that a fair description of what's going to happen in a week? Yeah. It's not how to lie with statistics. That book has already been written, but Yoon will teach you about some typical mistakes in early study of statistics. And now to my longtime friend and colleague, Martin Flashman. Marty was here when I got here, so that'll sort of date him. He's been here many years before I got here. I do know Martin got his PhD at Brandeis University some number of years ago. It was a while ago, but since I've known him, and this does go back almost 25 years, he has studied what at first he called transformation figures, a way to understand functions. But I think transformations and figures are so widely used, he's going to use, or you've come to this new term, mapping diagrams, same kind of thing. And as you can see up there, he's going to take on, for you, for all of us today, calculus and complex variables. So please welcome Martin Flashman.
On NPR, there's more about ums and ahs. So if you get bored, you can count the number of ums and ahs that I do and see if they have any meaning to it. Sorry about that, I messed around this morning. If you have some kind of technology with you and you want to, you can go to that website and you can actually interact with the same things I'm interacting with the pictures and diagrams that I'm going to be showing you. These were all made with GeoGebra. I should acknowledge that, but it'll be clear in the work. And I want to thank Craig for putting together the poster for this. And so these are snapshots from what we're going to see today. You can't make them out too well because they're kind of fuzzy, but they'll be much clearer later on, and I hope they'll be better understood. Not only just clear. The idea of mapping diagrams to visualize function has been a theme that I've been following for a long, long time, and last fall, before last fall, I spent the whole term working on some materials for mapping diagrams, and I've got those linked here at the bottom here, but I'm just going to take us right to it, these references. So if you really want to get more about this, you can watch there's two webinars that I did, one for just on mapping diagrams to understand basically linear functions, and then another one I did for understanding trig functions. And that's about my materials are not up to that yet. The basic materials I have, mapping diagrams from algebra basics to calculus and differential equations, A, B, C, D, E. That reference resource book is still in progress this fall. I didn't make as much progress on it as I hoped on the middle section, but I've been working on the calculus part of it. I think that's what it looks like. That's the front page of the materials. And if you want to read some backgrounds or explore this more carefully from the get-go, that's a good place to start. Back to where we are here. There's also a more philosophical treatment of mapping diagrams that I gave in the fall of 13 at the computer-based math summit run by Mathematica. And I gave a presentation there on concepts to drive technology in the 21st century, because a lot of technology is there, and sometimes it's there without any reason except I can do it with the technology. And what I'm trying to do today is put some concepts behind the technology. So the stuff I'm doing with the technology here is there because I think the concept of the mapping diagram as a way to visualize the concept of function is a very valuable and powerful tool. And if you want to see how I do this in various parts of the calculus course, I have materials in the sensible calculus program, which is about 30-some years old, which currently Henry Matsumoto is working with me on, and sometimes at least. And so that's it. Now you might notice some of these things, these little markers here, and that's going to pitch us to where we're going next. So here we are. My first slide. What's a mapping diagram? So, how many people here know what mapping diagrams are already? Okay, so there's still people who could be informed a little bit more. So, I think you're all familiar with the idea of a function, and I'm going to use the example. The function is determined by the rule. It takes the number x, and it gives you back the number minus 2 times that number x plus 1. That's the function I'm going to use for this example. It'll show up maybe later, and over here, I think, is a table that you can make with a spreadsheet. Actually, this is in GeoGebra, and GeoGebra has spreadsheets built into it. So this is a spreadsheet in GeoGebra, and I put in this spreadsheet some numbers input, numbers from 3 to minus 1, minus 1.8, I guess. And it's interesting. And these are the values that come up when you put those numbers into the function. So these are the function values, and that's the first way that one might encounter a function. It's just a lot of data collected input and output. Now, many of you are aware of the fact that this kind of function, minus 2x plus 1, will give a graph. If you look at the ordered pairs, you'll get a graph of a function. These are all the ordered pairs, and of course, it's not just the discrete ones that are on the table, but they've filled in a gap somehow. There's an illusion that there's actually a line there. Actually, it's just a lot of pixels turned on, and it's not actually continuous, but it gives you that illusion anyhow, like the illusion that I'm in front of you, when in fact it's just an image that you're seeing in your eye, and transfer it to your brain, and somehow you believe that there's an actual person here. Same kind of thing with that. You get this illusion that this is an line, when actually the data we have is really much more discrete, and not to say it doesn't do some things on the side. Over here is a way to visualize it. It's what I call a mapping diagram. And you can see that at 0, the value is 1. Look over here, 0, the value is 1. So that's what's showing up here. And if I move this up a little bit, you can see that as I move the x's up, the value of the functions moves down. And if I come up to 3, or somewhere around 3 and move it down, it'll go back up. And you can see how this arrow, pointing from the input to the output, is also being marked over here on the graph. So this arrow, with first x value of minus 1.86 is here. That's the first coordinate at this point. And the second coordinate, the coordinate on the second line, vertical line here, that's my, if you like, y-axis. That's 4.72, and that's the second coordinate at this point. So this arrow between these 2 points on these 2 axes on the right corresponds to this single point on the line on the graph. So this is our Cartesian way to visualize the function and the ordered pairs, and this is a mapping diagram way, and we can see it dynamically by moving it up and down. We can see that as the x, start low, as the x goes up, the values of f of x come down. We have a way to visualize that here. I also have actually all the data from the table visualized with all of these arrows. And so you can see how, if I move this through the arrows, you can see how that's really sort of just tracing out selected pieces of the data, and you can see those pieces of data are also here in the graph. So those data correspond to this. And in making the graph, the more data you have, the more you get the feeling like it's a line. I can reduce the data here by having 7 pieces of data or 6. So I control the number of data here with this n slider. and the B and A are telling us where the data is being selected from. So if I start off at, if I go from B is 3, that's where from -3 to 3, you can see that this is down here at the data is -3, and it's going up to 3, and the outputs are coming up here at the appropriate numbers. -3 is 7, and 3 is 5. So you can see those numbers over here much more clearly identified in the table. So that's the data that's being represented on the graph and on the mapping diagram. Anyone have any questions? If you have any questions during the talk, just feel free to shout them out and try and, of course, raise your hand would be nicer. But if I'm not noticing you, just call out because it's going to get a little bit more techy as we go along about the math. So I do presume that you have all had calculus. Everyone here has had some calculus in the back, one semester calculus? Okay. This is my clicker. This is yes, and this is no. Okay? Yeah, I can't hear it, but I can see it. See the data right away. Okay. So that's the basic thing, and mapping diagrams are ways to visualize what's in the table and can also give us an understanding what's happening in the function by seeing it more dynamically as the x's go up, the y's are going down, and the x is going down, the y's are going up. Okay, so that's mapping diagrams. Linear functions are a very important part of all mathematics. They're very important before you get to calculus, and they're even more important when you get to calculus because it's the basic model that calculus is trying to understand functions with. It's saying, what if this function, whatever function we have, what if it were linear? All right? Now there's two aspects to a linear function, and linear functions are traditionally expressed with an equation that says that the value x put in, you multiply that by some m, which I call a magnification factor, and then you add some b. And actually, you can think about it as a composition. We're not going to do that today, right away, but you can think about it as first multiply by m, then add b. And that's the way you can think about this linear function. If you're technically correct, the linear part is the mx, and the b is really some kind of affine change that's happening to that linear thing. But put that aside. There are two important numbers here, m and b, and we're going to see how those numbers appear, not just as, in the traditional way, the slope of the line, which I have over here. I have a line here with slope, m is 2, and b, that's the value at 0, is 1, so you can see that point right here. When x is 0, y is 1, this goes over 1 and up 2, so that's the slope. And I'm going to actually show you that slope, but over here we have a mapping diagram, and it's also set at 0. And so the value at 0 is 1, so you see that over here. That's our initial value. And we don't see the slope right away, so I want to show you the slope. So the slope can be interpreted as the magnification factor, but right now it means if you change the x by 1, you change the value of the y by that amount times n. So if I change the x by 1, we'll see I change the y by 2, because 2 is our slope, our magnification factor, m. And the change in y is 2, and the change in x from 0 to 1 is 1. And if I change this, these stay grouped together, so you see that that's giving us the traditional way to see that the line is actually, the slope is the same at every pair of points on the line. And in the mapping diagram, it's the ratio of the change in y to the change of x, that's always the same, even when it's not 1, but that's visualizing our slope. Now, there's one other feature, because we see the slope visually as something about a line, but in the mapping diagram, that slope, that feature of the slope, is not present in the picture. It's the ratio of the change in y to the change in x. But there is a visualization that happens, and I'm going to show it to you right now. It's called the focus point. It's determined by the m and the b. Here it is for this. It's a point back here. You see where these two arrows, if you extend them as lines, where they meet back here, that focus point, and you can do some of the geometry to see why, that point will be the same no matter where I move this. Watch this as I move the point now. See, the focus point stays the same.
With your first example with negative slope, it was very clear because it was between the
Yeah.
source
And
and
now
target.
I'm going to do some of that. So let's see, if I change the B, what's going to happen to the graph? Well, if you change the B in the graph, the line moves up and down, right? They're parallel. Let's see what happens when I change the B on the mapping diagram. So the focus point moves up and down on a vertical line because that's that line is what determines the, if you like, projection or the magnification factor in the similar triangles that are appearing in this part of the diagram. So the magnification factor is determined by on what vertical line that focus point is with regard to the two lines that we're using. So let's put the B back at 1. And now let's see what happens when I change the slope. All right, so if I change the slope, that's the magnification factor. If I make the slope bigger, well, on the line, on the graph, that means the line's going to get steeper. But if we think about it as magnification, if I make M bigger, I'm going to magnify things more. And so the focus is going to move closer. All right? So here I have this magnification factor of 4. And say, well, where's the 4 here? Let's just move this around and see the 4 pretty easily. This is 4 to 1. That's the change in y is 4 to the change in x is 1. So that's our magnification factor at this point. Okay, but what happens if I take the M and move it back down now? We were at 2, so let's move it back to 2. Now let's move to smaller numbers. Now if I move smaller, I'm going to get less magnification, so the focus point is going to move away. It's moving away. It's out of sight right now. And at 1, the difference between the change in y and the change in x is the same. So what we have in the mapping diagram is a little parallelogram here. A little parallelogram. And so the point is not in the picture the way we see it. It's gone off to infinity. Now the infinity is really hard because there's infinities that way and there's infinities that way. And it's actually at both of them. And we can see it's at both of them. It's a little bit hard to think about, but it's at both of them. And you can see that because if I go smaller than 1, all right, so now we take a smaller than 1, we can see that if we bring that in, the focus point comes over on the other side as we shrink the interval with magnification smaller than 1. You can see that shrinking. And then, the best of all slopes, 0. But that's really hard to see because the slope of 0 just means it's a horizontal line. But here's the meaning of the slope of 0 as a function. The focus point is the point of the value, and no matter where I choose this, it's giving you the same value. So no matter what time it is, no matter what the x is, it's giving me the same output here. And that's a very different way to interpret the magnification factor than, oh, it's a horizontal line. This is saying, in terms of motion, it's not moving at all. It doesn't move at all. There's no magnification. It's just going to one spot and stays there. All right? If you think about that in terms of the time being kept track of on our x thing, time being kept track of by the x, and our position on the vertical axis being kept track of by the y, then it says if your magnification is 0, then you're not moving at all. Okay, you have 0 velocity. Zero velocity. So in terms of motion, we can think about this ratio not as being a number, but as a rate. And that's a very good way to think about the magnification factor here, is that it's really a rate. You think about it as distance is rate times time. So I have a time, multiplied by rate, I get a distance, and I add it to my original distance, and I get my new position at various times. Okay, so I think that's the quick review. Not so quick, but the review of linearity. Linearity is at the heart of the calculus. So,
negative slope? No?
Huh?
Not going to go negative on the
Oh, I
slope?
just this, of course. Here's the negative slopes. There's -1. That's crossing right in the middle, and you can see these are congruent triangles, but flipped over. And so as the x goes up, the y goes down, and they're pivoting on that focus point. Thanks for reminding me of that. And if the m is less than -1, we get magnification. And as we get closer and closer, larger and larger negative, we get closer and closer to the x-axis here. Focus gets closer and closer to the x-axis. And again, just to show you, that's, if you change the b, it just moves that point up and down in the same vertical line. And if we ever got the focus point on the x-axis, we'd be in deep trouble because there'd be no way to move, magnify it, do anything. And that wouldn't be a function anymore. Okay, so if the focus gets really close to this, it's a very extreme, close to the x-axis, it's either very large magnification positive, if it's on the positive side. On the left-hand side of the axis, it's positive magnification, very great. If it's on the right-hand side of the axis, it's very large magnification with the opposite orientation, if you like, all right, opposite direction. Okay. Now, before we get to the calculus, I thought I'd say a word about limits. Now, this is, I had to do a little fixing in this thing to make it start off right, but one of the things when you talk about limits, let's just put this here for a second. When you talk about limits, you say, well, I'd like to know, here's my function, it's 2x minus 1. And I'd like to know, and I can change that over here, but 2x minus 1 here. So I'd like to know, so some of these applications that I'm doing here with GeoGebra, you could use for any function. You could take this and say, I want to study the function, instead of studying 2x minus 1, I want to study the sine of x. Or something. You just put that in here, and then you can study the sine of x and its limit properties as well. So in this one, I'm looking at 2x minus 1, and I'm thinking, well, what's the limit as x gets close to 1 of 2x minus 1? And I'm saying, is it 1.5? So here I'm using 1.5. I can change, this is my guess. What's the limit going to be? Oh, let's try 1.5. Or 1.49, 1.5. Let's say it's whatever, 1.65. Okay, maybe that's my guess. Is that the limit? So if that's the limit, then when I take the x and make it close to 1.5, I should be getting close to 1.65. When I take the x close to 1, I should be getting close to 1.65. Well, it doesn't look like it's close, but if you think about how close I want it to be, well, if I only want to be within 1 of it, I am within 1 of it. So I'm looking at the values over here, and I'm saying I'd like the value to come out of the function to be within 1 of 1.65. So it could be as big as 2.65 or as small as 0.65 if it's within 1. And it does seem to be within 1. So maybe that's okay. How close do I have to be before I can guarantee that we'll be within 1? So I'm going to show you now. Let's put this out for 1 here. There's a lot of values within 1. So all the way from 0 to 2. Those are within 1 of 1. And we can see that they're not close enough. So if I make it a little closer, you know how close the x's are to the number 1. So let's get them within a half. No, it's still not close enough. But, oh look, if I make all the numbers that I put in within 14 hundredths of 1, then all the values that come out on the right-hand side are within 1 of 1.65. But if I say I want to be closer to 1.65 than just 1, if I make this smaller, let's say I want to be within a half. Let's say that much, 0.54 of 1. So 1.65. So up and down exactly that amount. Then the question is, well, can I always guarantee, if I make the delta small enough, can I guarantee that I'll be within that close to 1.65? So let's make it, it's clearly got stuff outside. Well, wait a second. All this stuff here, over here, that's not going to get close at all. No matter how small I make this delta, and I'm going down pretty small, Now none of it's inside there. Right? None of it's inside. So there's no way I can get a delta that's close enough that will make the interval close enough to 1 so that everything will be inside the interval that's only a half away from the supposed limit. So that's not the limit. So what do we think the limit is? Well, we take this off for a second. Let's hide all this extra stuff. I think the limit should be down here closer to, well, the limit's closer to 1, isn't it? So let's take it down to 1. All right, so is the limit 1? Now I know we all know the limit's 1. You're all familiar with that. But let's see if we can work that with this epsilon. So I've got an epsilon as 0.54. How big a delta do I need before I can guarantee I'll be in there? So here's some deltas. This is a third. That's too big. Well, it looks like a fourth will work. So if I want to be within 0.54, it looks like everything within a fourth will work. What if I make the epsilon smaller now? Let's take it down to maybe a tenth. There's a tenth. How close do I have to be to the 1 so that all the numbers will come within 1/10? Somebody, anyone want to suggest?
0.05.
0.05? Okay, well, we'll try that. Let's see, I don't know if I can get to 0.05. I get down. I think that's more than you need.
Oh, is it? I went with the reciprocal of your slope, which usually you have to use.
Yeah. Okay. But there's clearly, if I go a little bit closer, like at 0.04, clearly all the arrows are inside. So that's a way to visualize the basic idea of limit. It's not talking about over here on the side here, that the rectangles that are dealt with in the calculus usual textbook approach. You choose the epsilon, that's these lines. I choose the epsilon, that's those lines in the graph. And then I have to find the delta, that's those lines, so that all the values of the graph sits inside of the box, basically. But this is a different way to think about it, and it's a little bit closer to the way the statement of the definition is. And I'm going to see if I get the definition. It's showing up down here. I can pull it up. Here's our definition of the limit. It's a number. It's a number so that given any epsilon, you can find a delta so that if the x is between a minus delta and a plus delta, then the number f of x will be between L minus epsilon and L plus epsilon. So that's the standard definition. All right, so that's one way that these mapping diagrams can be used to visualize things in calculus. And that's not new. If you look at some of the traditional calculus books, older calculus books like Spivak's calculus book, that picture is used for that book, and it's also in some other calculus books for a long time. So let's look a little bit more at other ways to think about the calculus and the mapping diagrams. All right, well, here's the typical thing. What's the definition of the derivative? Okay. Well, usually the derivative is defined by this limit right here. By the way, these are the nice formats here are coming through MathJax, which is a nice way to write nice math in HTML. You can use tech to make it work. Write the formulas in tech. So this is the usual kind of definition for the derivative. It's a limit of quotients. So it's got that limit idea in it. It's got quotients. The quotients are thought of as the slopes of secant lines. So here's the secant line in this picture. And over here we have, well, we have 2 points. So we have magnification factor for those 2 points, so we can find the focus point for that magnification factor right here. And so we can think about that point as representing that secant line through the 2 points. Okay? So we got that, and if I change, now this is, I'm using h here, but that's just controlling the delta x. So if I make that smaller, you get secant lines getting closer and closer to one particular line. These are, the h's are positive. Let's flip it over here to the negative side. Here's some secant lines here. Here's our focus points showing up now in the mapping diagram. So, as the h gets closer and closer to 0, the slope of the secant line gets closer and closer to the slope of the tangent line. The secant line looks more and more like the tangent line. And what we're talking about really is, if we think about it as velocity, we're getting the average velocities getting closer and closer to the instantaneous velocity. And the other way that people think about it is that we're getting the linear function that best, the slope of the linear function that best approximates the actual function at that point. And so when I take this to 0, everything disappears. Because we know when we have no difference in the denominator, we get a meaningless thing. There's no tangent, there's no secant line, there's no focus point, because it's just one line. You can't have two lines in a second to get a focus if you just have one line. But there is a tangent line, there's the tangent line, and there is a focus point that tells us about the linearity here. And if we put back, we move this back off, we can see now what's happening with not only the tangent lines, but if you look at the focus points, as we move the h closer and closer to 0, the focus point for all those approximating linear functions gets closer and closer to the focus point that is the focus point that represents the derivative. Now the derivative here is, for this function is at 1, I think we're at 1, so the derivative should be 2, and so that point here should be magnifying it up there, and take that out. Show off. So at this stage, I put on something else besides the focus point. I put an arrow here. Because the derivative is not only telling us a focus point, it's telling us how far we'll go in 1 unit of time. And so if I draw the line from this focus point to that, this line arrow here has a length of 2. And that represents the derivative at that point, and it's a vector. It's pointing up. That means we have a positive derivative. If it were pointing down, we'd have a negative derivative. And I'm going to try and move this x down to -1. And there it is at -1, and you can see that the focus point is here. Focus point is there. Take off the second range step. The focus point is there. That's giving us a magnification of -2. And you can see that the arrow there is pointing down. If you went up 1, you'd be hitting the end of that arrow. That's a range of 2. So that arrow pointing down is telling us what the negative number is. One of the things I'm talking about in count 3 is the fact that everything you learned about numbers in count 1 is really the same, except that we have to